Hi everyone, welcome to the day 11, I guess, of our Mini-Astro-workshop series 2020. So today with us we have Devarshi Choudhury, who just recently completed his master's in physics and astronomy at University of Amsterdam. And he has also recently joined the same university, the University of Amsterdam, where he just recently started his PhD, mainly working on nicer data and neutron compact objects like neutron stars, on which he's going to talk more during the lecture today. And he did his bachelor's from Christ University in Bangalore. And I mean, when I looked at his CV, I see he has a lot of experience dealing with compact objects and their observations in astrophysics. Uh, so coming to the research experience, he has even looked at recoiling supermassive black holes, wherein he was trying to see if one can actually uh, observe or find any recoiling supermassive black holes uh, in ASIANs. And uh, I think for the past few months or year or so, he has been working on the NICER data. So NICER, he's going to talk more. It's a telescope which is present on International Space Station, which actually observes individual neutron stars. So far, most of the observations that were made of neutron stars are mainly in a binary and not much of an isolated neutron star. But NICER for the first time can actually let you observe an individual neutron star and probe its structure and everything. So essentially what I'm trying to say is that it's very crucial. The telescope that's present on ISS, which is NICER. And I mean, uh, apart from NICER, the only other way to really constrain some properties of neutron star is gravitational waves. So it's a very, very, very important telescope, guys. And the data that we get out of it is also very important. So it's a very important telescope. That's what I'm trying to say for studying neutron stars. And apart from this, he has also been an astronomer for some time during his bachelor's, he was telling me, wherein he was actually uh, trying to look at, I guess, classifying the B stars uh, at Vainu Observatory, if I pronounce it correctly. And also, while after his bachelor's, I guess, he was at Tata Institute for Fundamental Research, wherein he mainly looked at the pre-main sequence stars. I mean, as you have heard in the recent star formation talks, before a regular star forms, there is a precursor protostar kind of thing, right? Like before the star actually enters the main sequence. Even we understood that during the lecture on stellar evolution too. So he was trying to kind of see or observe such pre-main sequence stars in young open clusters. And I see he has also some experience with using the code called MESA, which is a famous software to do stellar evolution with all the physics and other complications input. So he was trying to reproduce the Betelgeuse observables. I mean, recently Betelgeuse has made the news a lot because people were thinking that it may undergo supernova, etc. So fascinatingly, he did work on producing the Betelgeuse observables. Maybe if there's time, he can comment something on the chain variation in the light curves of Betelgeuse. And he has also published two papers. One was on astrometry, the foundation for observation astronomy, as a review. And the other was comparative study of different stellar tracks and isochrones. And he has also given multiple talks and has been doing these kind of outreach activities since a long time. So personally, I very much like to listen to this talk because I myself work on neutron stars. I'm really looking forward to this talk. I hope you all do. So I think with that, Devarshi, you can kick it off.
Yeah, sorry, I got muted. Okay, so I'll try to share the screen. Let me know. Is it visible?
Yep.
Okay. So, okay, good evening, everyone. everyone. I'm Devarshi Choudhury, and I am a first-year PhD candidate here at the University of Amsterdam, and part of the Anton Pannekoek Institute for Astronomy that they have here. And I work with the NICER Science Working Group, and we are trying to study compact objects and probe the particularly neutron stars and try and understand what the nature of dense matter is inside them. Can you see the full writing here? Is this being blocked by the Zoom panel? Can someone tell me?
No, I can see the compact objects, dense matter, everything, and even
Okay, perfect. Okay, cool. Okay, so I should begin by talking about death stars. Oh, sorry, that's not what I meant. I meant death of stars. Okay, so since a star is born, it has a life cycle where it evolves and then eventually dies. And this evolution process was covered recently by Aman in his lecture on stellar evolution. So that's not something I'll go into. I'll focus instead on their deaths. The death of stars is a fascinating phenomenon, and they lead to the formation of some of the most exotic and mind-bending objects in the universe. The kind of object that forms depends on how massive the stars are once they've formed. So for a low mass stars, it will go through a red giant phase, form a planetary nebula, and the remnant will be a white dwarf. But if this is also the fate for most stars, including what will happen to a sun. But if the star is more massive, then it will go through supergiant phases, and then explode in the form of a supernova to give us either a neutron star or a black hole. If the star is supermassive, then it might even skip the supernova phase and directly form a black hole. But before we explore how and why these objects end at such different stages, once they die, I want to touch upon the scale of these objects to get an understanding of how weird they truly are. Okay, so they're called compact objects for a good reason. On the top left image here, this is an artist's illustration of how massive a white dwarf would be. And you can see that it is about the size of Earth, but it weighs about the mass of a sun or even more, making them incredibly dense. So it's so dense, in fact, that if you were to take a spoonful of this object, then it would weigh as much as a family-sized car, a sedan or something. On the bottom picture here is an illustration of how big a neutron star is. These are typically the size of an average city, let's say Bangalore, Calcutta. In this picture, they've shown Vancouver for scale. And they weigh around 2 to 3 times the mass of the sun. So they are much denser than even white dwarfs. And if you took a spoonful, they would weigh as much as Mount Everest or even more. In this talk, I'll refrain from speaking about matter inside black holes because calling them dense matter is an understatement. Whether they're even in a material form is unknown. And so we'll only focus on things that are observable for this talk. This picture, many of you might have guessed, is taken from the movie Interstellar, by the way, which performs some excellent simulations. Okay, so as you've seen in previous lectures, the star is stable against its own gravity. Why? Because of the nuclear fusion processes that are taking place inside their core. The fusion processes, they are subject to outward gas pressure, and the fusion process leads to radiation being emitted, which interacts with the surrounding material, and this applies a radiation pressure. So this combined effect, it takes care of, it provides an outward pressure which counteracts that of gravity. So once the star is born, it is happily fusing away hydrogen into helium at its core, but life is not a bed of roses. There comes a stage where you start depleting the fuel. And so what happens? The gravitational pressure starts to dominate. And once it starts dominating, the core begins to contract and it heats up as a result, assuming that we are in the ideal gas regime. So there will be a rise in temperature. And once it's high enough to ignite helium, another fusion stage begins with helium burning in the core this time instead of hydrogen. And that in turn forms carbon and oxygen and other things in the process. So now let's consider the case of the low mass regime, that is your typical star like the sun. So in the case of a low mass star, once you've started forming carbon and oxygen in the core, the temperature again like before isn't high enough to ignite them. And so the gravitational pressure begins to dominate. So this again leads to core contraction. But unlike before, it does not directly relate to a rise in temperature, and there are some interesting consequences to this increase in pressure. So to explore what actually happens, let's recall Heisenberg's uncertainty principle. So what it states is that you cannot measure the momentum and density of a particle simultaneously with a precision greater than or equal to h bar by 2. So as we increase the pressure, the distance between the particles, particularly the electrons, they begin to decrease. So the space between them decreases, and like their position in space becomes more and more well defined. This leads to an increase in the momentum as a result, and momentum is in turn linked to the energy for these particles. In this case, that will be the Fermi energy, and the Fermi energy in turn starts to increase. And we say that the electrons have now become degenerate. What it means is that the Fermi energy of the system is much, much greater than the thermal energy, which is given as kT. So T is the thermal temperature here. We must also keep in mind that there's Pauli's exclusion principle that we have to consider, which states that no two fermions can exist in the same state. So you cannot pack more than 2 electrons in a given energy level, provided they have opposite spins, of course. And this, like this is better illustrated in a picture. So let's say you have a system where you have a wide enough, which is pretty tight, but you still have a big enough del X, and all the electrons, they will start occupying the lowest energy levels that they can find. And they'll populate all these levels all the way up to EF. But as you compress them further, instead of a rise in temperature, the energy levels, the value of the energy levels themselves start increasing, and it exceeds kT. And again, as I said, because of Pauli's exclusion principle, these electrons on the upper levels cannot populate the lower levels, and this sort of exerts a counter pressure, and this is known as electron degeneracy pressure. So I want to look at, so let's take a look at the effects of this degeneracy pressure, and that is quantified by the equation of state. The equation of state is just a set of equations that relate pressure, temperature, and density. But as we saw before, the rise in temperature is negligible, and the rise in Fermi energy is massive. And so as a result, the system can be effectively considered to be in zero temperature in comparison. So the temperature is removed from the equation, and we are only going to focus on the effect of pressure with respect to density. So first, let us look at a non-relativistic case. So our Fermi energy, it is related to the momentum as pf squared by 2m naught, where m naught is the rest mass of the particle. Now the pf, which is the Fermi momentum, it is related to the number density, that is n by v here, to the power 1 by 3. And so we can equate them, and we find that Fermi energy is related to the density to the power 2 by 3. Now, how does this affect pressure then? Well, the pressure is proportional to the internal energy of the system, which is given as the total number of particles n times the energy of each particle, that is the Fermi energy. And so you get this relationship that the degeneracy pressure is proportional to density to the power 5 by 3. But Chandrasekhar, when he was deriving these things, he noticed that if you keep on increasing the Fermi momentum, there comes a point where the momentum becomes comparable to mc, the speed of light. And so relativistic effects start kicking in. What happens in such a scenario? Well, we'll only consider the ultra-relativistic scenario here, where we assume that all the particles are relativistic in nature. And from Einstein's equation, we can get an expression from Fermi energy as momentums times the speed of light. So the Fermi momentum we already saw was related to the density as 1 by 3. And this time the energy, because there's no square dependence, also is related to density as 1 by 3. Again, we go through the very same steps, and we find that the degeneracy pressure, which was previously proportional to density to the power 5 by 3, is now proportional to density to the power 4 by 3. Okay, fantastic. Why does this matter? We can always equate this degeneracy pressure to the outward pressure from gravity and see if they were to be equal, what we would find. So this is a first order differential equation, and Chandrasekhar had solved this for both the cases. And he found that for the non-relativistic scenario, which is when you have 5 by 3 dependence, you get this relation of the radius being proportional to mass to the power -1/3. So that is this blue line here. So as you keep increasing the mass, the radius decreases and decreases, and then it sort of and then it sort of stabilizes after a certain point, and the decrease is nominal no matter how much mass you increase. But if you consider the ultra-relativistic scenario, then plugging that value in for pressure into the equation, Chandrasekhar obtained his famous limit, the Chandrasekhar mass limit of 1.4 solar masses. What he found was that when you hit this mass, the radius drops down to 0. So this is an object with no radius, but 1.4 times the mass of the sun. And this kind of gave concept to, okay, so black holes could indeed exist. Well, of course, as we'll see later, that other phenomenon kick in and we get a neutron star first. But this was a very important discovery for the time. So now I shall talk about Lucy in the sky with diamonds. And no, I'm not referring to lysergic acid diethylamide for those who understood that reference, but I'm talking about white dwarfs. So once you form this object that is made of degenerate electrons, you've got this very dense core. The outer parts of the star had expanded during the giant phase and are now gravitationally unbound. So the degenerate core is now, that remains, has typical temperatures of tens of millions of Kelvin. And this is much lesser compared to their Fermi energy. And these stars, they slowly radiate this energy by giving away light, and cools over billions of years to around the typical temperatures of stars, that is thousands of kelvins. And through this process, what happens is that the interiors, they are likely to solidify. And this solidification process happens under a very high pressure regime. And the end product is that we expect to find a crystalline structure in the interior of the star. And this is something that was evidenced recently by astroseismic observations of a star called BPM 37093. And they found that indeed the interior would be crystalline in structure. And since we expect these stars to be primarily made of carbon and oxygen, the interior would take the form of a diamond. Hence the star has been dubbed as Lucy in reference to Lucy in the sky with diamonds, which I think is brilliant. Okay, so that's it. That kind of covers white dwarfs. They are these degenerate cores of low mass stars that are left behind. What about high mass stars? Well, the immediate question that pops in that could pop in one's mind is what allows high mass stars to carry on fusing? You would have heard that high mass stars carry on fusion into much heavier elements. Why doesn't degeneracy kick in such conditions? And why is it only for low mass stars? Well, the more massive the star is, the more mass there is in the core. That means that the photons that are created during the nuclear fusion process have to undergo increased interaction with its surrounding matter. And through these interactions, it's actually imparting energy to this matter, and the temperature of the matter rises with the dependency of T to the power 4. So now let's consider, okay, let's term variable beta. So what we'll indicate with beta is the fraction of gas pressure in the system. And so the radiation pressure is the remaining amount, which stands for 1 minus beta. So soon after finding out the mass limit, the Chandrasekhar mass limit, Chandrasekhar went on and found out that if this radiation pressure fraction, if this radiation pressure fraction 1 minus beta is greater than 9.2%, then the radiation pressure is always going to dominate and the gas shall always remain classical. Why is that? Because the KT shall keep on rising so quick, much quicker than that of the Fermi energy. So let's analyze this statement in the form of this plot of equation of state, that is the relation between pressure on the y-axis and density on the x-axis. So on the blue line here, we indicate the relation that we found for white dwarfs previously, that for non-relativistic case, you have a dependency of density to the power 5/3, and for the relativistic case, the slope changes to 4/3. So if you have a low mass star, which is gas pressure dominated, that will be this solid red line here in the bottom. Let's say you have a gas pressure of 98%. So then you see that this line, it intersects with the degeneracy line at some point. And so the star becomes degenerate when you increase its density beyond a certain amount. Then and what Chandrasekhar found was that this dotted red line, that is when you have 9.2% radiation pressure, it coincides perfectly with this relativistic degeneracy slope. And so if you have stars that have radiation pressure more than this amount, so let's say I've got a 50-50 scenario, then the slope of this line is such that it will never intersect with the line demarcating degeneracy. They'll never meet. So no matter how much you keep increasing the density, it doesn't matter. The gas shall always remain classical. And that means that the temperature gets an opportunity to be high enough and ignite more and more of the elements into heavier and heavier elements. Great, so that's how massive stars are able to form from hydrogen, helium to carbon to neon, oxygen to silicon. And this process continues, and you get sort of this onion layering structure. But once you start producing iron in the core, that's when things get tricky. Iron is the most stable element. It has the highest binding energy per nucleon. And so fusion stops when it reaches, when you start producing iron in the core. And this fusion, the silicon burning to iron, it takes place at around temperatures of tens of billions of Kelvin. And at such high temperatures, there are a few interesting phenomena start kicking in. One is that at such temperatures, you start generating a flood of neutrinos via weak interactions. And unlike photons, neutrinos do not interact with matter very strongly, and they have a longer mean free path, so they are able to escape the system quite easily. So this allows for the system to cooling. It's called neutrino cooling, because unlike before, the radiation pressure has now, like the responsibility of the radiation pressure is now decreased. So you end up with a degenerate iron white dwarf in the center. At this temperature, you also have a phenomenon like iron photodisintegration. That is, you have the gamma radiation that's been produced, and they bombard with iron and even other particles and dissociate them into lighter nuclei and release a lot of neutrons. All these reactions, silicon burning and so on, they all usually take place above densities of 10 to the power 7 grams per cubic centimeter. And above such densities, a phenomenon called electron capture becomes important. Normally what happens is neutrons, they dissociate into protons and electrons if they're outside the nucleus. But in this case, the inverse happens, and the electron get captured by protons to give you neutrons, and it also releases neutrinos in the process. There's an interesting side effect to this. If you recall, the Chandrasekhar mass, it was obtained based on electron degeneracy pressure, and that was dependent on basically electrons, the number of electrons that are there. So again, so through electron capture, you now have a decreased number of electrons, and this in turn decreases the effective Chandrasekhar mass. So it's easier to cross this mass. There's if your star is extremely massive, you'll also have a lot of pair production in such scenarios, and you will generate electrons and positrons as a result. So all of these processes, they sort of kick in once you hit iron, and they happen in various degrees for various stars, depending on a multitude of factors, and particularly the mass of the system. But the end product is usually the same. That is, it explodes as a supernova. But let's explore why exactly. So once all these processes start taking place, they begin the dynamical core collapse of the iron core, and this is because of the drop in radiation pressure, and then the Chandrasekhar mass has dropped, and so as you keep fusing more elements and depositing mass onto the core, it's easy to cross that Chandrasekhar mass, and so the core begins to collapse. But because it's so dense, the inner core contracts quicker than the outer core does, and it quickly reaches densities above nuclear saturation densities, that is 10 to the power 14 grams per cubic centimeter. And above such densities, two very important things kick in. One is the neutron degeneracy pressure, which is similar to electron degeneracy pressure, but with neutrons instead. Another is strong force repulsion between the nucleons. So what happens is this effectively stalls the core collapse all of a sudden. And this causes the cores to bounce back. But remember that the inner parts, this is only happening in the inner parts, which have been contracting very quickly. The outer parts of this core, they are unaware of what's just happened, and they're freely falling. So this core inner part, which is now bounced back, it propagates a shock wave through the outer core and then into the outer layers. And initially, people thought that this shock is what drove a supernova explosion. But soon they found out that this shock would result in increased photodisintegration because this process consumes energy, which is provided by the shock, and it'll also result in increased electron capture. So that kind of stalls the shock. It kind of fizzes out. So how does supernova carry on then? Well, as the inner core was contracting to higher and higher densities, it actually got so dense that neutrinos kind of became degenerate. They got trapped inside the core, and they formed what is known as a neutrinosphere. So in this case, like even neutrinos had to undergo interaction with the matter around it significantly before it can escape. But once it does escape, it diffuses into the shock front, travels a bit, and then reacts to the material in the shock front, thus imparting energy to it. This energy refuels it and provides it the necessary energy to propagate throughout the star, and that rips the star apart and it explodes. So this explosion is phenomenal, and the brightness of such explosions can outshine the brightness of their host galaxies. And once this energy has dissipated over a couple of days, what remains is this beautiful nebular corpse of the system. This is Crab Nebula, by the way. And in the center of such nebulae, at the very center, you would find the degenerate core that is now left behind, which is a neutron star. This image is that of Cassiopeia, which was taken by Chandra in X-ray. Okay, so these processes were very dynamic and violent, and you had all these different layers of the core behaving differently and being subject to different densities and pressure regimes. So as a result, the neutron star, unlike what the name suggests, isn't simply composed of neutrons. It has a more layered and complicated structure to it. And so let's explore how the neutron star, what it's made of. So we start with an atmosphere, and why is there an atmosphere? Well, after the explosion, the supernova explosion, one second. Yeah. So after the supernova explosion, some of the matter might not have been able to escape. They might have fallen back into this gravitational well, and they would have been stripped down to their bare minimum, which is forming, and so the heavier parts would have just sunk into the neutron star, while the lighter, and so you're left with like partially ionized or fully ionized hydrogen, helium, and so on. And after the atmosphere, you hit a solid surface of the outer crust. During this core collapse, because the densities were so high, the iron core, the iron nuclei that remained, they formed into a solid ionic lattice, and this is embedded in a sea of degenerate electrons. But as you go deeper, these electrons undergo capture with protons, and you get heavier and heavier nuclei as a result, because of increased neutrons in the nucleus. So coming to the inner crust, this is usually demarcated by what's known as a neutron drip point. So on the top, you can see, like, let's say you have the outer crust, and there is a limit to how many protons to neutrons you can have in a nucleus. And if you exceed this limit, the neutrons start to essentially drip out of this nucleus, and you enter a system which is filled with what's shown in red here, which is supposed to indicate the superfluidic neutrons, and you have these nuclei that are scattered in between them. But as you continue to go deeper into the inner crust, you'll see that these nuclei, they come closer to each other, and they almost start touching. And as they touch, they sort of form these blobs, which are called, like, they're often called as meatballs or nuclear gnocchi, which is a kind of pasta. And as you go deeper, these blobs also coagulate together, and you start forming these elongated cylindrical structures, which are called nuclear spaghetti. Go deeper still, these nuclear spaghetti then transform into nuclear lasagna. So this entire thing is called nuclear pasta in literature. And then finally reach this point, which the demarcation point between the inner crust and the outer core, where densities are as high as the nuclear saturation density. So you cannot sustain such nuclear structures anymore, and you basically end up getting a sea of homogeneous nuclear matter. But now you have superfluidic neutrons stuck in between in places in anti-pasta phases. So this was pasta, and this would be the opposite of that. So this is an anti-pasta phase. So this is the outer core. And if you keep going deeper still, then that is something that we cannot really predict what's going on based on our QCD calculations and based on first principles. Up until this point, you could still simulate based on what we understand of the nature of matter as to what will happen. But under such high densities and such high pressure regimes, we don't exactly know how the strong force behaves. We don't know whether the neutrons and protons, whether they'll just be in their superfluidic or superconductive states, or whether they'll dissociate into their component quarks, or they'll restructure themselves into forming exotic states like hyperons and so on. And this is something of great importance as a result. This allows us to probe into like what's going on in the center and what the nature of matter is like. So this diagram, this is a phase diagram for dense matter, and you've got temperature increasing on the y-axis here, and density, which is given as a proxy of this quantity here, increasing on the x-axis. So ordinary hadronic matter would lie in the bottom left side of this plot. The LHC and other such particle accelerators and colliders, they usually try to probe the high temperature, low density regimes of matter and how they interact in such conditions. These kind of mimic the conditions that were in the early universe. So you get like things like core-gluon plasma. What is unexplored is this side of this plot, which is the high density, low temperature. Low temperature again, because the Fermi energy is much higher than the thermal temperature, and it's effectively at 0. So the neutron stars probe this particular part of the diagram, which otherwise we have no idea of knowing how matter is supposed to behave. And this is all very important because this gives us further insight into how these forces actually behave, how particles interact, and they help us make deductions for particles that are spread throughout this plot. Okay, so how would we do that? How can we possibly study the interior of a neutron star? These are objects, remember, that are the size of cities, and like we barely manage to zoom into the surface of the moon. How can we study neutron stars? Well, lucky for us,
Devarshi,
it turns out.
Maybe we'll take a small break here, right now.
Yeah, okay, this is a good point. Yeah.
So I'll read the questions from the chat. So guys, you all can post the questions to the chat, or you can raise your hand. Okay, I see Shreyant Singh has raised his hand. Yeah, go ahead.
Can I ask the question, or maybe the?
Yeah, you can.
I just wanted to go to the previous slide.
Yeah, 1 second. This one?
Yeah. So what is the width of the inner core?
Okay, so the inner core is usually, I think it's usually about a few meters in size, so around let's say about 10 meters or so. It's very small, but it's ultra dense. Yeah.
And we are trying to probe even the inner core using. Since I do not have an exposure to this field, I am just interested in knowing we are also going to probe the inner core of the neutron star using some technique.
Yes, so that's something that we cannot infer from theoretical calculations, and the only way we can study them is by actually observing different phenomena of the neutron star that I shall cover in the latter half of my talk. As for the outer layers, like you can still make theoretical predictions, and then based on different kinds of observations, you can check whether the theory is likely to be true or not. But for the inner core, there's just we just don't understand the things well enough to predict anything.
The outer core can be described efficiently by strongly interacting QCD, meaning quarks and the soup of neutron, proton, and electron, which is strongly interacting, is some setup of the soup which is strongly interacting. We are sure that we can describe the outer core well.
Yes. So, so the thing is, like in case of the inner core, there's these things like there's a fermion sign problem that prevents us from making these QCD calculations, which we can make for the outer core. So we can make theoretical predictions for what's going on here. Something that I want to touch upon, for example, this nuclear pasta, anti-pasta phases. Like these are also things that would have effect on the radius of the neutron star. With like they would affect the radius in such a manner that we would be able to pick them up using observations. So that's something that we do to try and correlate our theory with observations. Yeah, but so otherwise, these are strong force QCD calculations that enable us to predict what's inside.
Okay, thanks a lot.
Next, we'll go to the questions in the chat. So Prachus is asking what happens to the vast number of electrons once a neutron star is formed. The protons get converted to neutrons, right?
Yes. So, the electrons that are there, they. I'll go back a few slides. Yeah. So you've got this equation here. That is the electron capture equation. So the electrons and protons, they combine and they form the neutrons. So most of this electron is depleted into forming neutrons and also neutrinos. And these neutrinos are also responsible for driving away the for reigniting the shock front, as we saw, because they are usually trapped within the core. So yeah, most of it is converted into these two things.
Next, Atharva is asking, can someone explain about how star quakes occur? Maybe you can answer how neutron quakes, something.
Well, we don't really see star quakes on neutron stars as such. Like we are not that sensitive. Our observation is not that sensitive. People do try, as I said, to perform astroseismic observations for white dwarfs. That's how they found out that it's made of carbon. But I'm not the best person to really answer about why these quakes occur. Like there are these oscillations. There are these things called G-mode oscillations, and they sort of resonate the structure, and the structure sort of vibrates, causing star quakes. But I am not the best person to answer this. If anyone else can handle it, I'll be happy to.
Yeah. The next is Nitesh is asking how the supermassive stars skip supernova phase.
Yes. So okay, right. That's a very good question. So in normal circumstances, you have this situation where the core is collapsing, and then you hit neutron degeneracy, and you experience strong force repulsion, which prevents further collapse, right? But in the case of supermassive stars, like the mass is just so high that even these forces are nowhere near strong enough to stop the collapse. The density is just that high. So you don't create this shock front. You don't create this kind of a situation where you have supernova like that. Although there are predictions that it is associated with like it could be associated with gamma ray bursts and other phenomenon, but it's not your typical supernova, to say the least. You immediately form a black hole.
Next, Ayush is asking, presence of hyperons in the core of neutron star. Can this be a reason for fast cooling of such objects?
Fast what? Sorry, fast cooling.
Yeah.
I think you might be confusing cooling here with that of like its dependence on Fermi temperature. Because when I say these objects are cold, or when I say that these objects are cooling, I mean that the radiation that is trapped inside them, they are being released, and I believe they don't have anything really to do with hyperons. But maybe I am misunderstanding the question.
I think they're trying to maybe come from the perspective that having a different composition in the core or around outer core, etc., that can actually affect the opacities and in turn affect the...
Okay, in that sense. Right, yeah. Well, I'm not sure if this, like how really this affects the cooling of the star. That's not something that I have studied. But yeah, I suppose these would affect the opacities of the structures in some way, and how quickly light can escape, radiation can escape and cool them down. But I'm not sure whether hyperons would accelerate or decelerate the cooling. I cannot answer that, I'm afraid.
And next, Divyanshu is asking, how do we come to understand the presence of such pasta in the neutron stars?
Right. So these are, again, purely from calculations. These are purely from simulations that we have drawn these deductions. We are like these calculations are not plagued with uncertainties that come up to, when we are studying the inner core, and so we kind of rely on these calculations to tell us what kind of structures these will assume. And also, as I said, like they try to observationally confirm these theoretical pasta predictions by looking at the radius of these stars and seeing whether like how much they've been affected. In the absence of pasta, they would be much smaller. Also, the pasta phases are quite important in terms of how they like how much like they are able to trap neutrinos more efficiently. So the supernova shock front, it relies on the escape rate of neutrinos from the inner core, and that is again dependent on this pasta structure. So that is something people are trying to look into and see whether they can confirm the presence of these pastas somehow. Another interesting thing that we are trying to observationally do now is like if these pasta structures, if they take on large enough, if they become large enough, they form large enough lumps, let's say about the size of hemisphere, then there would be quite like there would be a mass, like you would have more mass on one side of the star, and like these would be pretty massive objects that are spinning continuously as the star is rotating. And so they would be sources of continuous gravitational waves, and that is something LIGO might be able to pick up, and people are trying to do that.
I think just to add to that, correct me if I'm wrong, I think based on the spinning down of these neutron stars, I think one can actually predict using glitches and the rate of the spinning down, whether such a pasta phase actually exists, because it in turn affects the superconductivity and
Yes, indeed. That is also another aspect in which they try to infer that yes, indeed, these pasta phases exist. But these are mostly thought of through computer simulations.
Yeah. Next, Bharatwas has his raise hand. Yeah. Go ahead, Bharatwas.
Yeah. Sorry for the interruption. Correct me if I'm wrong. Actually, what I've read in my high energy course structure, like while I was studying high energy, so in that neutron star cooling is related to like that neutrino cooling, which are which have two processes: direct URC and modified URC. So
yes.
So I think what she means is like the neutron star cooling. So is that related to that the same, like because central of neutron star cooling is very much taken care of by the neutrino cooling, and after that some stage it went off to the thermal cooling, like black body radiation.
Yeah. Okay. So yeah, that is correct. And so these ARCA processes, they especially play a major role in driving this supernova shock front, and that these processes do carry on even after the neutron star is formed. So yeah, like you have these forms of cooling take place.
Okay, so, these depend on the stiffness of the neutron star, like how much stiffness the neutron star has. So is there any other process like we can define neutron star cooling? Like,
well, I mean, these are the dominant forms. I'm not sure if there are other processes that people are exploring as to how it cools. But yeah, these are what's usually considered as standard forms of cooling.
Okay, thank you.
Yeah, next up we have a question from Divyanshu. He's asking, so do we have any experimental verification of such faster region or any plans in LHC or somewhere else?
Yeah, so as you mentioned, like through glitches and through radius measurements, we can, of course, infer the presence of these past stars. And as I was mentioning, that because they would be massive and dense rotating bodies, they would likely be sources of continuous gravitational wave emission. And these could be picked up. Oh, wait, did you say LHC or did you say LIGO? I'm not. I thought you said
LHC.
LIGO. Oh, LHC. Sorry. I assumed LIGO. No, I do not. I would imagine these would not be probed by LHC because if I go back to this diagram here, so LHC, like, it probes high temperature conditions, and they're nowhere near as dense as what you find in neutron stars. Neutron stars have densities typically even higher, like of nuclear densities and higher.
Yeah, you can go ahead. That's all.
Okay, so we covered that. So to recap, this is what we are trying to now probe, the inner core, which we cannot theoretically predict. So how do we do that? Well, lucky for us, it turns out that the dense matter physics, whether it's neutrons or hyperons or deconfined quarks, they dictate the equation of state of the neutron star, which is the relation between pressure and density, as we saw. So here we are dealing with supranuclear densities, that is densities above the density of an atomic nucleus. And so based on, so let's say if you have got a quark family of matter existing there, it would have a certain kind of relation, certain equation of state. If you've got nucleonic, it would be different. If you have hyperonic, it would be different. And these are only some of the possible forms of nucleonic, quark, or hyperonic equation of states. There are many more of these kinds as well. So now the equation of state, the pressure and density relation, they are in turn related to the mass and radius of the star. So if you plug pressure and density into the TOV equations, the stellar structure equations, similar to how we did and found out the Chandrasekhar mass, you can plug them here and you get this relation for mass and radius for the different equation of state models. So it basically boils down to the fact that if you have accurate mass measurements and accurate radius measurements, then we can use those to confirm, okay, this equation of state applies or this one doesn't apply. And mass and radius, because these are such dense objects, they define how the space-time around the neutron star is, how bent this space-time is. So the radiation from the neutron star surface, as it travels through this bent space-time, this information is encoded in it, and this we receive in the form of X-ray data that we can analyze. And by analyzing them, we can trace back all the way to the dense matter that is inside. So previously, there have been attempts, of course, at measuring the mass and radius. And they're usually obtained from X-ray binary studies. So an X-ray binary is when you have a compact object, like in this case, one of them has to be at least a neutron star, and the other companion, if it's a wide dwarf, then it's a low mass X-ray binary, or it could be massive stars, in which case it's a high mass X-ray binary. And when you have such binary systems, we have well-established orbital dynamics, relativistic orbital dynamics. In non-relativistic case, you'll have Keplerian dynamics, and here you will also have to account for relativistic effects. So based on these, we can accurately determine the mass. So orbital dynamics is probably something I think Surendra might cover in more detail in his upcoming lecture. But basically, this allows you to calculate the mass of the components involved with very high precision using radio timing measurements for pulsars. Pulsars are just rotating neutron stars. Radius measurement, however, is a bit trickier because these objects are so small, like it's hard to actually measure them from their angular width. You cannot just find out its angular width and use it to obtain the radius. Instead, you have to rely on spectral modeling, and people usually perform the spectral modeling when this X-ray binary system, this low mass X-ray binary system, it is in a quiescent state when it's not very active, or when during its outburst state. So these variations that occur, that they allow measurement of radius in these scenarios. But one of the important things in this case is that you have to assume an underlying spectral model for the emission coming out of the neutron star, which is not exactly black body. So and we are uncertain of exactly what kind of spectra we are going to be looking at. And this introduces a lot of uncertainties in this technique. And there are also many other underlying assumptions associated with them that prevents us from obtaining radii that, like the different results that we obtain, they don't necessarily match with each other. And there's so this is a big problem. If we don't have radius, we cannot trace back to the equation of state, and we cannot trace back to the core composition. So in comes a new technique called pulse profile modeling. So I shall describe this technique by the means of this clip here. So on the left-hand side, let's consider a rotating neutron star, and let's just turn off gravity for a second. Also throw in a hotspot on this surface. I shall describe why these hotspots exist later. But let's say there's a patch that is emitting brighter than the rest of the star. So as the star rotates, the brightness due to this hotspot increases and decreases as it goes out of view. And there's an eclipse. There's an eclipse here. But a neutron star is a strong gravity regime, and in such cases, relativistic effects become important. So first of all, there is light bending. The space and time around it is curved, and there's light bending, and so the star appears bigger than it actually is. You can see areas from behind the star. Both the geometrical poles in this clip is visible as a result. And you might have a situation where the hotspot never completely goes out of view as a result, and you never experience an eclipse. You always have some brightness contribution from the hotspot as a result. Second thing is that these are actually rotating very fast. They are called millisecond pulsars usually, and they rotate at a few hundred to few thousand hertz. And as a result, they have pronounced special relativistic effects like Doppler boosting. So as the hotspot goes in and out of view, when it's coming into view, that is the arriving side, is blue shifted. And being blue shifted, the peak luminosity is reached sooner than it would be in the normal if there was no such effect. And as it recedes, it gets red shifted, and as a result, the overall result is that this pulse waveform gets skewed. And so the higher this spin is, and the higher the mass is to radius ratio, which is known as compactness, the higher this ratio is, the more bent the spacetime is, the more modulated this light curve is going to be. So if we have accurate enough phase information, if we can chop them up into different time intervals or phase intervals, then we can study these effects really well, and through them we can probe into how strongly bent the space is, and if we know how far it's spinning, then we can arrive at the mass and radius values. So pulse profile modeling is the founding principle for NICER, and we do that using a software called X-PSI, which stands for X-ray Pulse Simulation and Inference. X-PSI is a software that was developed by a senior of mine, Tom Riley, and Tom developed this with Anna Watts. And the way it works is that you take in a model for so you take in details of the instrument, and you receive this X-ray data from the neutron star. You plug in a model for the neutron star, how the space-time around it is, where the spots might be, and then you compare what kind of model suits the data by a process known as sampling. So there's a bit of statistical sampling involved here. And through the sampling method, we thus arrive at the neutron star parameters. And this whole process I shall get into more detail now, starting with the instrument and data. So for the instrument, we are using NICER, which stands for the Neutron Star Interior Composition Explorer. And this is an X-ray telescope that is placed on the International Space Station. It's this metal shaped box here. These are all the X-ray detectors in black. And you can see it's on the International Space Station. You've got these giant solar panels of the ISS. So NICER is designed for pulse profile modeling, and it's meant for observing. It's meant for observing soft X-ray. It's highly sensitive in soft X-ray. Why particularly soft X-ray? And by soft, I mean low energy X-rays, because that's where the maximum output of rotation powered pulsars is. Like the hotspots of rotation powered pulsars, they dominate in soft X-ray. I shall come into this term soon. And they also, NICER also has a very high time and energy resolution, which is required for performing detailed pulse profile modeling and acquiring inferences that are sensible. So so I was talking about rotation powered pulsars. These are the primary candidates that NICER observes. So the rotation causes a dynamo effect, which in turn maintains the magnetic field for these neutron stars. These magnetic fields are usually immensely strong, and it's not completely known why we have such strong magnetic fields. One theory is that there is magnetic flux freezing, which is that the original magnetic strength of the massive star is now contained within this tiny blob, and so it has very strong magnetic fields. But that does not completely explain its field strength, and so this is also an open problem that people are trying to work on. Nevertheless, we do know that these exist based on pulse observations in radio, in X-ray, that are caused by charged particles that are being stripped off the surface of the neutron star by the magnetic field, and they are deposited onto the other end of the pole, which and this bombardment releases soft X-rays. So this soft X-rays is what we're trying to observe using NICER. So this is an example data set of XMM Newton, which is an X-ray imaging and detection telescope on top. And this is NICER on the bottom. And you can immediately see that the rotational phase bins are way more well-defined than in XMM. And also NICER has a larger collecting area for the photons. And so you get a lot more data. The counts per bin is much higher than you get in XMM. So such data allow us to perform a good level of pulse profile modeling. Okay, so we have covered the instrument and data. So now we need a model for the neutron star. So there are many aspects to this modeling. I shall only talk about the important ones here. So let's say you've got your typical neutron star here, and what we are most interested in is the emission angle. That is, this is normal to the surface, let's say, and the angle at which the photons are emitted. And once these photons are emitted, because the space-time is bent around it, they'll get deflected as it reaches us. So the observer is at infinity. This angle that between the normal and the received photon is the deflected angle. These are two important things that we have to consider. And how do we do this? Well, we consider a model for the space-time of the neutron star. Now, if it's a static neutron star, if it's not rotating, a Schwarzschild metric would be good enough to define it. But these are rotating rotating neutron stars, and these rotate at very high speeds. So you've got extreme special relativistic effects. The exact solution for such a system, computing it can get very, very expensive. And to do this over and over for different models, it's not a very feasible option. So instead, what we opt for is an approximation, which is shown in this dotted line here, that matches pretty well with the exact solution, which is this thick black line. The approximation that we use is that we consider that the Schwarzschild metric is defined not by a completely spherical object, but an oblate object. It becomes oblate because of its rotational, it gets rotationally deformed. And we also account for the Doppler effects in particular. So the combined answer is pretty close. So this is the kind of space-time that we plug in, and that's how we use it to trace how the ray is going to behave. So this is known as relativistic ray tracing. The other key thing that we have to consider is where the spots are on the system and what is the geometry of the spots. So recently, the results from the first ever observed target of NICER, that is Pulsar J0030, was released by two groups. This is by Riley, my senior who developed the software. And the way he went about modeling these is that first you consider a simple model. Let's say you've got two circular spots of the same shape, same size, and they're diametrically opposite to each other, and we call it antipodally symmetric. So, and on top of this, we apply the neutron star model, the space-time model as we described before, and we try to see what happens. But these are found to be insufficient, and so we add more complexity to these models. So some things that we can try to do is, instead of making it a uniform single temperature spot, we can make it a dual temperature spot. Let there be a certain amount of variation. And the other thing we can do is that they need not be diametrically opposite to each other. Maybe the magnetic field structure is such that these spots could be elsewhere, not be opposite. Further complications were added down the lane, where the presence of rings were explored. This could also be a double temperature structure. Instead of being like uniformly concentric like this, it can be a bit skewed. Even more complexities were explored, where you can have a crescent shape like this. You can put in a, instead of what we call a hole here, we can also plug in another temperature material here. So you can affect the complexity of these models in various ways. And as we do this, you have to keep in mind which of these complexities are actually useful in defining the data, and which of them are getting overly complex with minimal increase in our model performance. Okay, so now that we have our models that we can test with and our instrument and data, we have to go ahead with sampling. Now, sampling is based on Bayes' theorem that was covered by Ish in a previous lecture, but I shall recap it because many of you might not be very familiar with this. So this is Bayes' theorem, where you've got posterior in terms of the prior, likelihood, and evidence. So I shall take you through each of these terms to get a better understanding of what they are. Starting with the prior. So prior is basically an educated guess. It is the probability of theta, which is our which are parameters like, let's say, mass and radius for a given model. And this is the probability that our model is going to have certain parameters. And then we have a likelihood, which is how likely is it to observe the data with such a parameterized model. So if you've got, let's say, a radius of 10 kilometers and a mass of 1.4 solar mass, how likely is it that we would get such data? There is the evidence, which is a normalization term, because the product of this has to be rounded to 1. And how we do that is we consider the probability of the data given all sets of parameterized models. So no matter what kind of parameterization you choose for this given model, what is the probability for the data? That is the evidence. And finally, the thing that we are most interested in is the posterior. That is the probability distribution of the parameters given our data and model. So we have already described the models and we have our data. So what are the parameters that we will end up with? This is what we're interested in. This is what you're trying to find. How do we do that? So we do that by a technique called nested sampling. In nested sampling, you consider an n-dimensional parameter space. So to keep it simple, let's consider a 2-dimensional parameter space of θ1 and θ2. So this could be mass and radius, for example. And so you define this sort of a prior volume for that space. And in that prior volume, you instruct the computer to, okay, I want to draw a bunch of samples, a bunch of points in this prior volume. And the computer does that. And then we task it with finding the point with the lowest, points with the lowest likelihood in this, among the ones that are drawn. So let's say that is L1, that is the lowest likelihood contour. And then we say, okay, so we don't want points that are unlikely, so we want points with higher likelihood. And so we want points that are only within L1. So we again do the same thing. We draw a bunch of points within L1 and find the lowest likelihood. We find L2. We repeat this process to L3, to L4, and we get this sort of a nested structure. And therefore it's called nested sampling. Now, for the more experienced audiences, nested sampling can be sometimes more algorithmically efficient than MCMC, that is Markov chain Monte Carlo techniques. And in n-dimensional parameter spaces, you can have multimodal distributions. You can, this is one mode. So this is like one hill that's going up. So you could have a combined hill here. So we use a multimodal nested sampling software called Multinest to discern these things. Anyway, so these processes, they can get quite computationally expensive because you have so many parameters, and for each of the parameters, you're drawing, let's say, 1,000 samples at each iteration. And you're calculating all these different things for them. You're calculating the how the model is going to behave. And it gets very, very computationally expensive. So we need high performance computing system. And for this purpose, we use the Cartesia supercomputer, which is the Dutch national supercomputer here. So having performed sampling, we obtain our posteriors, and which gives us idea of the neutron star parameters. So I shall talk about the results that were obtained by Riley et al. 2019 as they progressed through more and more complex models and removed the models that were overly complex. They arrived at this model as being the final. So this is unlike any dipolar canonical picture that you have seen in your textbooks. You don't have two diametrically opposite uniform poles. You have one circular spot and a spot that is in the shape of an elongated crescent. And the posteriors obtained using this model were, well, these are the most precise simultaneous mass and radius measurements that have been obtained to date. Something that I forgot to touch upon before, the previous mass and radius measurements, they always relied on the neutron star having a binary companion. And this study was performed for a star that is isolated. So there was, in normal circumstances, you would have no other way to find out what its mass and radius are. So not only did we find mass and radius together, that's something that is not done usually. We found it for an isolated system, and we found it for with an unparalleled precision. So you get these sort of contours. This is let's say this is your radius distribution. This is the compactness. This is your mass distribution. And you can see you've got pretty tight constraints. As I was saying, the sampling processes can get quite expensive. About like I think 20 parameters here that you have to sample through, and you get posterior distributions for all of them. You have things like distance, you have things like interstellar extinction, and so on. So the model is then used to regenerate what the data would look like. So on top left here, this diagram, this is the pulse profile, which previously we saw things like on the right, where you had time on the x-axis and brightness or counts on the y-axis. Here you have time or phase on the x-axis, energy on the y-axis, and the brightness of the counts is shown in the form of a color bar. So yeah, this is the original data, and this is what was produced by the model. So, and then these are and the data is then compared with the model to see what the residual look like, if there is any structure in this residual which would indicate something that the model is not being able to explain, and so on. So, and the residuals are found to be fairly low for this model, and that's how you progress from one model to another. On the right here, on top, we have the actual data for pulsar J0030. And on the bottom, we have that generated by the model and the errors associated with them. So you can see that it's been able to mimic the data pretty closely, generating these two pulsations which overlap to an extent. Right. So coming to the work I'm doing, the present work that we have undertaken, that is for pulsar J437. So J0030, like I said, it was quite a good finding, but it did not fulfill the purpose that we were aiming at. That is, it's still too wide. This is the mass and radius distribution, and you cannot really cancel out one equation of state family over the other. Maybe this one is towards the extreme, but it barely tells us anything. So the next star that we are going to study is J437, and J437 is the nearest observed millisecond pulsar. As a result, you have excellent distance constraint, and you have many more counts. So if you take a look at the pulse profile on the right, you can see that the counts go up to around 65,000, which is much higher than the previous one, where the counts were around 30,000. So you have a lot more data to work with, and you have improved distance prior. Another big thing associated with this is that it is in a binary. And so you have a very tight mass and inclination prior from orbital dynamics. So the mass prior that we have on this from radio observations is really tight. And based on the work that we've been doing already, we are expecting by the final model to have constraints approximately 2 to 3% constrained on the radius. So let's say something about this size. And that would likely be able to confirm which of the equation states could possibly apply. So stay tuned for the results, which is probably going to be going to be published sometime next year. It's something that we've been working on and hope to be done soon. Okay, so scope for the future then. Once we have finished with O437, the current pulsar we're working on, there's another interesting candidate, pulsar J0740, which is the highest mass neutron star that has been discovered. And so that is something we'll be studying, and we'll see how the equation of state behaves when you have such high mass systems. And further ahead in the future, we can start observing accreting sources using future facilities like EXTP and Strobe-X. So this plot here on the left, top left, this is an effective area plot. What it means is that the collecting area of X-ray photons on a telescope, they actually depend on the energy of the photon that is being received, and they also depend on different telescope factors. So the actual area is slightly lower than the geometric area, and that is termed as effective area. So in this case, the yellow dotted line here, that is the effective area for XMM. The NICER has a much better collecting area in green, and you can see that they kind of overlap. And then you have EXTP in pink and Strobe-X in black. So they will also have a soft X-ray component with a very large collecting area. But more importantly, they'll also have they will also be able to collect photons in the hard X-rays. And this is where accreting sources usually peak in the X-ray luminosity as the accreted material is being bombarded onto the surface. So by studying accreting sources, we can get a better grip on the equation of state. Another thing that's going on, there was GW170817, I think, that was a double neutron star merger. So neutron star mergers also can provide us insight into the equation of state. As these objects are revolving closer and closer to each other, they get deformed greatly, and the level of tidal deformability, that kind of gives us an idea of how stiff, how compact the equation of state is. And so we can combine gravitational wave data and of the neutron star mergers with the equation of state constraints we get from these observations. And this will hopefully provide us better insight into what the nature of matter is in the center of neutron stars. So that's it for my talk. Thank you very much. If you have any further questions, please go ahead.
Hi, Devarshi. Yeah, thank you. Thank you very much for the talk. It was really interesting. So guys, if you'll have any questions, you can raise your hand. But before that, there are some questions in the chat. So far, yeah, maybe Devarshi, you can try to stress the point more as to how we can probe the interior of the neutrons to the core using the mass radius measurements and the equation of state.
Yeah, so I'll go back to the slide where it's a lot of slides ago. Yeah, so we're collecting this extra data. We are using this novel technique called pulse profile modeling, and we're finding the mass and radius, right? So once we have a good enough mass radius measurement, it would allow us to select which of these models are possible, which of these models can explain such a massive star with such a radius. So let's say we get a mass and radius with a probability distribution about this big, hypothetically. And so we would be able to say, okay, so it belongs to this relation. What is this relation? It is the equation of state relation given by nucleonic matter, or it could have been something else. It could be quark or hyperonic. And so you're able to constrain which equation of state applies. And what the equation of state depends on, it depends on the dense matter physics. If it's nucleonic, it'll have a different equation of state. If it's hyperonic, it'll have a different equation of state. And so by constraining the equation of state, you can finally figure out what's going on in the center of these stars.
Thank you for that. Hope it answered some of the people's questions here. And apart from that, there's a question from Bharadwaj Ayushi. There might be such relativistic effects on the jet from pulsars, right? Due to spin. Can we observe that? So I think the relativistic effects, they have it on the spots, right? So similarly, they're asking, can such an effect be there on the jets from the pulsars?
Yes, of course. I mean, if you have got an accreting system, you'll most likely have a jet formation in such scenarios. But the thing is that we need emission from near the surface of the star, because we need to capture the full extent of how much the space and time is bent around it. And so oftentimes these jets happen from a much higher layer than the neutron star surface. And also we need it to be in X-rays. So usually for, let's say, in accreting systems, when the material that is deposited onto the surface, that bombardment creates hard X-rays. And we can actually study these X-rays, but we can use it again for pulsar fan modeling, but there will be a lot more open questions associated with it, because we wouldn't know how stable these sources are. So they could be varying in their brightness based on how much material is being accreted. So until we have better understanding of the physics that goes behind accreting systems, it's a bit harder to perform the same technique for accreting sources. And that is something we are hoping to improve upon before we launch, before we are ready to analyze the data that comes in from future X-ray telescope missions like EXTP and STROBE-X, which are meant to observe such accreting sources.
And just to add to that and answer also some of the people's question, one has to remember when there's a binary neutron star system and there's a merger and there might be a jet associated with it, usually whenever people refer to the jets, they're rather referring to the structure that is pretty far away from the surface, where the particles are being accelerated to highly relativistic speeds, and that is what produce the relevant electromagnetic counterparts, and that is what's seen as a jet. But yeah, so that is usually different from the surface phenomenon that might happen around the neutron star surface. And as rightly pointed by Devarshi, I think those will be the ones which are highly get influenced due to the immense gravity. Okay.
Yes, exactly. So assuming you actually went and performed pulse profile modeling for something that is not on the surface, you would obtain a radius value that is much bigger than the radius of the actual star. So that will cause you problems.
Next, Bharadwaj. Yeah, you can go ahead, Bharadwaj.
Yeah, thank you. So as we can probe black holes from electromagnetic counterparts, from tidal disruption events, we can probe supermassive black holes. So we have detected many optical TDs for supermassive black holes to probe them. So have we ever detected TDs from neutron star, or are we looking to probe neutron star through TDs, like tidal disruption events?
Yeah, so are you talking about tidal destruction of two neutron stars, or like a massive star that is being engulfed by a neutron star?
Yeah, that is being engulfed by a neutron star. We have detected so many optical TDs to probe supermassive black holes. Yeah, tidal disruption events around supermassive black holes. So
okay.
are we also looking to probe something like for the neutron star?
Mm-hmm. Okay, so well, again, this will fall under an accreting system, right? And so this tidal disruption event that is happening, it's not like the companion star is being engulfed in one go. It's coming closer and closer, and you've got loss of angular momentum as this happens. And there are these phenomena take place where, called the Roche-Lobe overflow, which I'm sure. So as that happens, again, the infalling matter spirals around the neutron star, and then it's finally deposited onto the surface. And this deposition would, in turn, create X-ray emission in high energy X-ray emission, which but then there are many uncertainties associated with it, which we first have to address before we can observe such things. And once we do observe, we'll need better telescopes. We'll need telescopes that are meant for such targets. So like EXTP and Strobe-X, which are future missions.
Okay, thank you. Thanks a lot.
Yeah, no, sure.
Next, Shreyans, you can go ahead.
Yeah, thanks for the talk, Bhaiya.
Yeah, sure.
I just had a very okay. I'm just, so why are we trying to measure the mass and the radius? Meaning, why are we trying to probe the variation of mass and radius okay. And what TOV equation? If you could please let us know something more about it.
Okay. So the mass and radius are linked to the pressure and density relations that are taking place inside the star. Okay. So the way they are linked is through TOV equations, which stands for Tolman-Oppenheimer-Volkoff equations. So they gave these equations which describe the the stellar structure of a neutron star. And these stellar structure equations, they contain the mass and radius, the pressure and density. So if you find mass and radius of these stars, you can infer the pressure and density. And this pressure and density is dependent on what the core composition is. You will have a different kind of relation for nucleonic matter and exotic states. So that's why we are interested in the mass and radius. Does that answer your question?
Yeah, I had a related question. So in case of black holes, we find that the mass and radius, the variation should be constant because RS is 2 GM. I just wanted to get some insight, since neutron star is just very much close to being a black hole. Can we the very high mass regime of neutron star and try to understand where this linearity is coming from using equation of state?
I don't understand what you mean by linearity. Could you?
By linearity, I mean M is proportional to R. Meaning, why for a black hole we have a linear curve, while for a general star it can vary arbitrarily.
Okay. So as you're going to higher and higher mass neutron stars, there is this gap which usually between let's say theoretically around 2.4 to around 3, 2.5 to 3.5 solar masses, where you can we are not sure whether we would end up with a neutron star or a black hole. So this transformation to a linear relationship can be probed by studying very high mass neutron stars, indeed. As for whether this linearity exists for neutron stars, that depends again on the equation of state, and which equation of state applies is going to determine what kind of relation exists between the mass and radius.
Yeah. So any other questions for the speaker? You can post it onto the chat or raise your hand. Okay, I think Shreyans has a follow-up question.
Meaning, can we probe the equation of states? Have we probed the equation of states for very dense nuclear star, which can tell us something about where this linearity is coming from?
Are you referring to the fact whether we have studied such a high mass system, basically?
Yeah.
Well, not yet. I mean, we have using older, like we have studied, we have found out massive neutron stars, like J0740, which we're going to study after we are done with J0437, as I was mentioning. Yes. Well, J0740 plus 6620, it's the highest mass neutron star discovered. And this is around 2.15 solar masses, I think. I mean, obviously they have been studied in radio and stuff, but that's not how you get to the equation of state, not yet at least. And they have been, I guess they would have been studied using older generation of X-ray telescopes. So once we study them with nicer, we might have a better clue as to how this transition takes place.
And could you please let us know something about how this curve varies for a moderate size neutron star, and is there a phase transition, say m varies as r raised to power n1 to some r raised to power n2 as we modulate the parameters?
Yeah, so like there are these, so as of the moment, one of the things that we kind of assume is that there is a universal equation of state for neutron stars. This is something which is, I am not entirely sure why they assume it theoretically, but observationally this does not matter to us. And so one of the techniques that they try to use is that if you find a high enough neutron star, let's say something above 2 solar masses, right, then you would be able to discard equation of states that don't predict the existence of such objects. But then there's also a channel of discussion which says that you could have phase transitions as you're going from lower mass neutron stars to higher mass neutron stars, or as you're going as you're talking about different formation mechanisms. So in this particular figure, if you look at these blue lines, so these blue lines, they are supposed to represent these sort of hybrid states. So they start off as, let's say, nucleonic matter, and then once they're subject to enough pressure, that might depend on the formation scenario, then the very center of it can be transform into something else further down the line. So these are things that are like we don't have a proper grip on them yet, and these are things that we want to address by studying these equation of states. So so to answer your question, whether we can concretely say that completely differentiate between low mass neutron stars and high mass neutron stars as having different equation of states, that's not something we can do yet. That's for a later day.
Okay, thanks a lot, Bhaiya.
Yeah, any more questions? We'll take, I guess, 1 to 2 more, and then we'll end the talk. So you can post them to the chat or raise your hand as of now. Okay, I think there are no more questions. Thank you very much. Devarshi, like the talk was really interesting and it was very informative.
Thank you very much. It was a pleasure.
Yep, and it was very, very informative actually. Yeah. Okay, so with that, we'll end the talk. So if